Assalamu alaikum and welcome to lecture number 21. In this lecture, from this lecture onwards, we are going to start a new chapter. We will have new representation of the LTI system, namely the block diagram representation of linear constant coefficient difference equation and signal flow graph representation of the system. These are the new representation where we have these are basically two different representation which are pictorial representation of the LTI systems. Until now we have talked about the different representation or description of LTI systems, such as the system function representation or LTI system described in the Fourier domain, or the impulse response representation, or the linear constant coefficient representation. So you have a clear idea that the same system can be represented in different ways. In this chapter, we are going to explore one more representation, that is the pictorial representation or the structures. Basically, to implement a discrete time analog or digital hardware, the system must be converted to an algorithm or the structures. So we will talk about the block diagram representation and the signal flow graph representation of the LTI system in this chapter, to give you the idea that same LTI system can have different representation. So it's just the repetition. So for example, we have a system, LTI system of the first order, which has the system function as shown here. So this is the description of the first order LTI system using system function. So I hope that you are very well familiar with such equations, because we have done some these topics in much more details in the previous two chapters, that is the transform analysis one, and the second where was the Z transform. So I hope you understand that how we are going from the transfer function Z domain into the time domain, where we have the impulse response. So that's quite straightforward. This system function can be expressed in terms of impulse response. So this is the expression for the impulse response of this system. Again, this system can also be represented in terms of the linear constant coefficient difference equation. So we can find also the linear constant coefficient difference equation, which is written here. So these are the three different characterization or descriptions of the LTI system. So if we talk about the impulse response, so you understand in terms of impulse response, if we have a system described by impulse response, so the output of that system equals to the input convolved with the impulse response. So by looking at this equation, we understand that the system has impulse response that is of infinite duration. Now, if you want to compute the output over a finite interval, it will not be efficient to do so. That means using this impulse response, since the amount of computation required to compute the output will grow with n. So if we talk about the third equation, this one where we have described the LTI system in terms of the linear constant coefficient difference equation, we see that this provides an algorithm for recursive computation of the output at any time n. So if we carefully look at this equation, we have the previous values of the output, we have the present value of the input, we have the previous values of output, and we have the coefficients, multiplication of the coefficient. So if we further assume the initial rest conditions, then it means that the output will be the input will be 0 when n is less than 0, or for the negative value, or we assume that the input is causal, so the input will be 0 when n is not equal to n is less than 0. And similarly, we also assume that the output will be 0 when n is less than 0. So the system will be linear and time invariant. So this equation can be generalized to the order of the n to nth order, and you will see that we have different implementation for this equation. Okay, now to implement this equation, right, that is the constant coefficient difference equation, all we need is that you can observe that we need just adders, right, scaling, or the multiplication by a constant, and delay. So these are the three components that we need to implement such systems. So shown in the figure here is an adder. So I hope all of you are well familiar with these symbols, because you have done this multiple times in the previous courses which have been taught to you. But just as a refresher, the adder is represented by a circle with the plus sign inside, so x1, and the input is the other input is x2. Although here it has shown, we have shown here only the adder with 2 inputs, but adder may have any number of inputs. You also understand that scalar multiplications or constant multiplication or scaling factor is represented by a and just an arrow here, so xn, an arrow, and the value written over the arrow indicates the constant multiplier or the scaling factor. So we have axn, right? So where a is the scaling or the constant multiplier factor. And the third element we need is just the delay. So you understand we represent it by z, right? So z power minus 1, you understand that basically represents a delay by a unit. Okay, now for other than a unit, we can write it in generalize, that z power minus m, so m can have any number, right? So for example, delay by 2 units, that will be z power minus 2, and so on. You also know that if we have something like plus, that means, for example, we have z power plus 1, so z power plus means that you are advancing it. Okay, so also in terms of signaling system, you can say z power minus 1 means you are shifting it to the right, and z power plus 1 means that you are shifting it to the left. So I hope these are quite straightforward things which are basis for the pictorial representation or a new representation of LTI, right, systems. So let's consider an example. We are given the system function as shown here. So first let's express this system function in terms of linear constant coefficient difference equation. So you understand in a z domain, the output is equal to the response times the input. So simplifying this, because we are just multiplying h of z with it, which will result into y of z. So x of z multiplied by b naught 1 over a, right, this whole. So because this side is divided, so if I this thing is divided, so if I bring it to the other side, it will become multiplied. So I have written it as here. So this is equal to b naught x of z. Now taking the inverse z transform, it will result into this difference equation. Now to implement this equation in structures, you have on the previous slide we said that it can be into block diagram as shown here, and it consists of additions, scalar multiplication, and the delay units. So if you look at the right side of the equation, we have input which is multiplied by b naught. So this is your input. When we multiply at b naught, we get b naught times the input signal. Then this goes to the adder. So in the adder, if we look at, we have the previous value of the output scaled by a factor of a1. So this is the output. So output is delayed by 1 unit and scaled or multiplied by a1. So we get a1 yn minus 1. Again, this is 1 unit more delayed, and we get yn of y of n minus 2, and this the second one is scaled or multiplied by a factor of a2. So we have a summary here. So we get here at this point a yn minus 1 plus a2 yn minus 2, and this is added with the scaled version of the input. Thus we get this system block diagram representation. So as we said previously, the block diagram representation of the LTI system is a pictorial representation of the computational algorithm for implementing the system. When the system is implemented either on the general purpose computer or a digital signal processing chip, the network architectures and the network structures, such as the one shown here in figure 2, serves as basis for a program that implements the system. Also, if the system is implemented with discrete components or as a complete system with very large scale integration or VLSI technology, the block diagram is the basis for determining the hardware architecture. So by generalizing the previous example, which was just the second order system, now we generalize it to the nth order. So from the previous example, you can say that y of n minus summation k running from 1 up to n, ak y of n minus k equals to summation k running from 0 up to m, bk x of n minus k, and we denote it by equation 7. So the corresponding system function for this linear constant coefficient difference equation will be h of z, and h of z equals to y of z over x of z, and this is equal to summation of the inputs over summation 1 minus summation of the output. So you understand why we are subtracting it, why we have the negative sign here. So to write the equation 7 as recurrence formula for y of n in terms of linear combination of past values of the output sequence, right? These are the past values of the output sequence, and these are the present and the past values of the input. So we can say that because if you bring this into this side of the equation, it will become positive. So we can say that y of n equals to summation k running from 1 up to n, ak y of n minus k plus the inputs. So if we represent the inputs present and the past values, so we can say that we can denote it by v of n, and we say summation k running from 0 up to m bk. So if we denote it by vn, then we have yn equals to the past values of the output and plus the input. So to represent it in the block diagram, we can just say, because the input is the summation of the scaled version of the input and the delayed values, so we say okay, input because with the current value of the input we just have scaling factor of b naught, so input scaled by a factor of b naught, and then we have the delayed versions of the input. So I hope you understand. You delay it by 1 unit, then we have x of n minus 1, and we scale it by a factor of b1. So up to in this way we go up to m. So these all values are added to give vn. Again, for the output, we can say that output, if I delay it by 1 unit, I get y of n minus 1, and I scale it by a factor of a1. Similarly, z inverse scale, z inverse of 1 means we are delaying it by 1 more unit, so it will be y of n minus 2, and uh, so on, right? So to generalize it, we just say y of n minus n, this is equal to a n, and this is, we have the summation of all, right? So this is how we can generalize the uh, block diagram representation up to the nth order. Here we are, as we have represented it. A block diagram can be rearranged or modified in a variety of ways without changing the overall system function. So that means you can have different block diagrams for the same system function. Now each appropriate arrangement represents a different computational algorithm for implementing the same system. Same thing that you can use different block diagrams which represents the same system function. So that means the different arrangement will have a different computational algorithm for implementing the same system. So for example, the block diagram of figure 3 that we have seen on the previous slide can be viewed as a cascade of two systems. The first system representing the computation of the Vn, which is basically the summation of all the input values, and the second representing the computation of Yn from Vn. Now each system is an LTI, and if we assume the initial rest conditions, then we can cascade order can be we can cascade them in any order. That means we can reverse the order of the cascade as shown here. So in the previous slides, if you look at, we find this is V, and we find first this, and then we have this block, right? Whereas if we reverse the two, it will not affect because the two systems are linear. So here we are again doing the same. Here we are finding the omega n, and we are delaying the omega n and multiplying each omega n by some scalar. So that means at this point we'll have omega n minus 1, and we multiply it by a1, and similarly here it will be omega n minus 2, and we'll multiply it or scale it by a factor of a2, and so on, right? So by generalizing, we can say at this point we'll have wn minus capital N, and the scaling factor will be an. So similarly, this one is your, again, that is where we represented by this point by Vn. So that is your the input signal, you can see coming here. So the with no shift we have x of n, a b naught times x of n. With a single shift we have b1 x of n minus 1, and so on. So essentially this is the same diagram as we had on the previous slide, with the just change of the that in the previous figure we were calculating the zeros first. You understand these are the zeros and these are the poles. So there we were calculating the zeros first, followed by the poles. Now we are finding the poles first, and then we find the zeros. So if we write it mathematically, we can say h of z is the overall system response. So we say that h2 of z times h1 of z, and let we denote, these are, you understand, poles. So the factor, the term containing poles, we represented by, we denoted by h2 of z, and these are the zeros, and we say these are h1 of z. So Vz was equal to h1 of z times x of z. So this is right. This is the expression, mathematical expression for v of z. Again, y of z, which is the output of the system. So we multiply the out of the h2 of z with v of z to get the output of the system. So because the two systems are LTI, so that means we can interchange the systems, the order of the system, and still we will get the same output. So that means if we write h of z equals to h2 of z into h1 of z, or if we write h of z equals to h1 of z times h2 of z, it will result into the same, right? It will have no effect on the overall system function. So if we reverse the order, then we say, okay, we write the zeros and followed by the poles, right? So then we define another variable w of n, or in terms of in z domain we say w of z. So w of z will be equal to h2 of z multiplied by x of z, right? So this is your h2 of z, so which are poles. So this multiplied by x of z, we get w of z, and then we multiply the w of z with h1 of z, and we'll get the output. And you understand in both cases it will result into same because the systems are LTI. So if we write in time domain, we can say in time domain, so for w of z we will have w of n, and it is same as so it will be k running from 1 up to n summation, right? And ak w n minus k plus x of n. And similarly y of n will be equal to summation k running from 0 up to m bk w n minus k. So if I write it here, so this is the system of this one, where we calculate v of z first, okay, and then we calculate from using v of z, we multiply h2 of z with v of z to obtain the output, okay. For this second case, we first multiply h2 of z with x of z, okay. So this is for the second case. So you understand that omega in time domain w of z will be w of n. So this is the point where you get w of n. This is your input. So you delay the w of n by 1 unit, and you multiply it or scale it by a factor of a1, then you further up to n. So you get wn minus capital N into a capital N. So essentially it will result into same output y of n. The only difference is now instead of calculating instead of having the pole zeros terms first, now we have the poles terms first. Also in this figure we have assumed that m equals to n, that is the order of the poles, and the zeros are same, and still generalize, because if the order of the poles and zeros are not same, for poles to have higher order, the zeros will have coefficients equal to 0, and if the number of zeros are greater than the number of poles, then those coefficients of the poles will be 0. Theoretically, order of the implementation does not affect the overall system function, but we will see when a difference equation is implemented with finite precision arithmetic, there can be a significant difference between this two systems that are equivalent with the assumption that we are using infinite precision arithmetic. Each of the figure have m plus n delay elements. Also, if you note carefully, you can observe that here we have wn minus 1, okay, and again here we have wn minus 1. Here we are scaling it by a factor of a1, and here we are scaling it by a factor of b1. So that means we are using the redundant delay units, because again if we look at this one, here we'll have the signal that has value of wn minus 2, and again we have here wn minus 2. Similarly, if we assume the order of the both systems is same, then again here we are having wn minus capital N delay, and again here, so that means we are using the redundant delay units. So that means we can simplify them. So in short, we can say zeros of h of z are implemented first, followed by the poles in figure 3. If we find the difference between the figure 3 and figure 4. Also, poles are implemented first, followed by the zeros in figure 4, as I have also talked about it. So I think that's the summary of what I have said in the previous slide. So I will skip it. So collapsing the delays into one chain of delays will result into the system as shown here. So you understand, because the same signal omega n, it is delayed here and again delayed here. So why not remove this redundancy and collapse it into a single delay. So the number of required delay element will be reduced to half in this particular case. So if you look at this diagram, I hope that's quite straightforward. Again, you're just the input signal, it is delayed by a factor of 1. So again, it's delayed by a factor of 1. To the right side, we are scaling it or multiplying it with a constant of b1, and to the left side. So if you compare the two figures, you can easily notice that we have reduced the number of delay elements required. So definitely you understand that the two systems are performing the same function, but the one with the minimum number of delay elements is definitely preferred. So the implementation with the minimum number of delay elements is commonly called a canonic form implementation. So the figure 5 shows the canonic form of implementation of the block diagram. The non-canonic block diagram, as in figure 3, is referred to as the direct form 1 implementation of the general nth order system, because it is a direct realization of the difference equation written directly from the system function by inspection. The one shown in figure 5 is called the direct form 2 or canonic direct form implementation. From the previous discussion, we can say in general we have an unlimited number of equivalent realization of any given system. So as another example, consider a second order system with a system function as described here. So by looking at the system function, you can easily tell that the coefficients of the are b naught equals to 1, similarly b1 equals to 2, a1 equals to plus 0.15, and a2 equals to minus 0.9. I hope you understand the why we are writing here a1 equals to 1.5, because these have the negative sign. So if this has negative sign, so that means, because in formula we have negative, so that means if it is negative then it is positive. But if the symbol here is positive, because in formula we have negative, so that means actually it was negative sign. So I hope you will understand. That's not a very difficult point, but it's quite straightforward point, that in formula we have negative. So just like if you recall that we was doing the shift operation, right? So in shift operation we say if something has a positive sign, that means it is shifted left, and if something has negative sign, then it is shifted right, and if something has negative sign, that means its value is basically positive. Okay, so straightforward implementation. I hope you can straight away find the difference equation for this one. You just say, okay, h of z equals to y of z over x of z. So that means multiplying h of z with x of z will result into y of z, and that means this term will be multiplied with y of z, and then by taking the inverse of the Fourier z transform, we can straight away write the difference equation, right? Or let me quickly write it. So I think you can straight away find the difference equation from this expression. So to implement it in a direct form, one, we just say, because we have x of n, and it is delayed by unit and multiplied by 2, right? 1 plus 2 z inverse, so it will be z inverse into 2, and that's sum here. And then for the y of n, so y of n is basically delayed by 1 unit and then scaled by a factor of 1.5. Again, it's delayed by 1 unit and scaled by a factor of minus 0.9. So this is the direct form 1 implementation of this system. Again, we can so direct form 2 implementation of this one will be x of n delayed by 1 unit, and for the poles for the zeros we just straight away multiply it with 2, so here, and for the case of the zeros it will be for the case of poles it will be multiplied by 1.5, 1 unit delay again for the case of the poles, and then it's multiplied by minus 0.9. So that's the direct form 2 implementation for this particular system function. There's another pictorial representation of the LTI system called the signal flow graph. Signal flow graph is essentially same as the block diagram representation, except for few notational differences. Formally, a signal flow graph is a network of directed branches that connect at the nodes. Associated with each node is a variable or a node value. The value associated with the node K might be denoted by WKN. The branch JK denotes a branch originating at J and terminating at node K, with the direct form J to K indicated by the arrow head on the branch. So as shown here, so this is the node WJN, and representing the discrete time independent variable. So the arrow represents the direction. This is another node K, right? And we write it WKN, so it has some inputs and it has some outputs. Circle here represents the summation. So that means at Wjn, or the node J, we have two inputs and it has one output. Again, if we look at this one, the second node, which is K, we have two inputs here, right? So inputs are denoted by the incoming arrows, whereas the outputs are denoted by the outgoing arrow. So direction of the arrowhead basically tells whether it's the input to the node or it's the output to the node. So in summary, we say each branch has an input signal and an output signal. The output of a branch is linear transformation of the input to the branch. The simplest example is a constant gain. The linear operation represented by the branch is typically indicated next to the arrowhead, showing the direction of the branch. For the case of constant multiplier, the constant is simply shown next to the arrowhead. Similarly, when the branch operation is omitted, it means the identity transformation. By definition, the value at each node in a graph is sum of the outputs of all the branches entering the node. Source nodes are the nodes that have no entering branches. They are used to represent the injection of the external input, or the inputs or the signal sources into the graph. Sink nodes are the nodes that have only entering the branches and they don't have the output branches. They are used to extract outputs from the graph. The node variables are sequences. So let's have an example on the signal flow graph. So here we have a constant gain. So whatever here is, for example, x of n is here. So this means that we are scaling or multiplying the signal with the input signal with d. So let's consider the node W1n. So if we look at this one, Wn has input x of n. So we can write W1n equals to x of n plus this is W2n. So W2n times b is also input to this node. So we write plus w, in fact, let's start with a. So W2n, this W2n scaled are multiplied by a entering this one. Again, W2n scaled are multiplied by b is also entering this one. So we write x of n plus a W2 of n plus b W2 of n. Similarly, this is W2 of n, so it has only the one incoming, that is this one. So we say W2n equals to c, because this is W1n, so W1n multiplied by c is the input to the W2n. So W2n equals to c W1n. Similarly, the output node or the sink node is y of n, and y of n equals to has two inputs. One is the x of n scaled by the d. So y of n equals to dxn plus one input is coming from this side, that is W2 of n. So right, W2 of n multiplied by e. So y of n equals to dx n plus EW2n. I think that's quite straightforward, similar to the block diagram or similar to many other areas. I think you have done this in so many different subjects. So I will not emphasize here more on this one, and if you have any confusion, we can discuss in the live session. So let's consider an example for signal flow graph representation of the linear constant coefficient difference equation. You understand addition, multiplication by a constant, and delay are the basic operations required to implement a linear constant coefficient difference equation. And you also know that these are all the linear operations. So it is possible to use signal flow graph notation to depict the algorithm for implementing the LTI discrete time systems. Figure 10a is the direct form to realization of the system whose system function is given by this one. I hope from here you can find the linear constant coefficient difference equation. So this is the block diagram representation. Similarly, for the case of signal flow graph representation, we have this figure. So you understand this is node 0 or the source node where we have inputs, and this is node 5 or the sink node or the output from where we get the output. So by looking at the equation, we can note that the input is scaled by a factor of 1, and again the delayed version of the 1 unit delayed version of the input is scaled by a factor of b1. So we can write it like here. So you understand scaling is represented by arrow. So we have input is coming here because there is nothing on the arrow, so that means whatever you have here, we have the same here. Then so this is a node 2, and again we with the arrow we have written b naught, so that means the input signal is multiplied by b naught. Okay, so at this point we are delaying the signal by unit. So we have just written a delay branch here, right? So 1 unit delayed, and the 1 unit delayed scaled by a factor of b1, right? So this is your b1 x of n minus 1, which we get here. So for the case of the outputs, we have only scaling by a factor of a and delaying by 1 unit. So here we have already delayed the signal by 1 unit, and scaling it by a factor of a will result into a pi n minus 1. So that's the signal flow graph representation for the given system function. This is the block diagram representation, and this one is the signal flow graph representation. So we end the lecture at this slide, and we'll continue from this slide in the coming lecture. Okay, Allah Hafiz.